All right, hello. Let's take a look at our first example problem from Chapter 3. And just as a note before we begin, on the screen next to me, I have opened MATLAB, and then I also have opened the appendix from the book. So we won't need the seam tables in this problem, but just in case you need a unit conversion, we'll have that reference there available to us. So let's give it a try. So we're told that a gas is confined in a cylinder sealed by a piston 20 centimeters in diameter, whose mass is 30 kilograms. The pressure in the room is 1 bar. So A, what is the pressure inside the cylinder? Okay, so if I draw my schematic, okay, we have a piston cylinder apparatus where we're told that the piston has a diameter, or that piston head has a diameter of 20 centimeters, and it has a mass of 30 kilograms. Okay. The other piece of information we're given is that the pressure in the room is 1 bar. So my pressure is equal to 1 bar, right? And what I should probably write this is let me write this as the pressure of the surroundings or the atmosphere. Okay. So the pressure of my atmosphere or my surroundings is 1 bar. Okay, so in question A then, okay, what we're asked is what is the pressure inside my cylinder? Okay, so in part A, it wants to know what's the pressure inside my cylinder. So in my cylinder, I have this head, which is free to move, right, until I reach a state of equilibrium. Okay, so the pressure, right, inside my cylinder will be equal to my total external pressure, which will be equal to the pressure of the atmosphere, right, the pressure of my surroundings, plus the pressure due to my piston head. Okay. All right, so I know that the pressure due to the atmosphere or my surroundings is 1 bar. Okay, so then the question is, what's the pressure of my piston head? Well, the key is to remember that pressure is a force per unit area. Okay, so the pressure of my head, okay, is going to be equal to force per unit area. Okay, where here we're going to be dealing with the force due to gravity due to the piston head itself. Okay, so my force will be equal to that mass of that piston head, okay, M, times G. Okay, so force per unit area. What's the area? Well, we're told that the piston head, so we have a cylinder, right? So I have a cylindrical piston head with a diameter of 20 centimeters. Okay. So area of a circle is pi r squared. Okay, so if I simplify this out, we're given diameter. So my radius is 1/2 my diameter. So this should be mg over pi over 4 d squared. Okay. All right. So let's calculate it. So then the pressure of my head. So now as I calculate this, I'm going to make sure that I'm using SI units. Okay. So mass is in kilograms, SI. G is my gravitational constant. The only one I remember is 9.81 meters per second squared. That's in SI units. And then the diameter, it's given in centimeters, so we'll make sure we convert that to meters. So if I keep everything in SI units, then I know that the pressure I'll compute will be in units of Pascal. And then once I get that, I can convert to bar. Okay, so my pressure head, so we have 30 kilogram head. Acceleration due to gravity is 9.81 meters per second squared. Then in the denominator, I have pi over 4. And then for my diameter, right, we have 20 centimeters. Okay, so let me write a larger parenthesis here. So my diameter is 20 centimeters. And then I have 1 meter is 100 centimeters. So centimeters cancels, and then that quantity squared. Okay. All right, so let's do it. So let me label this as part A. So my mass was 30 kilograms. Then I had gravity, which is 9.81. That's meters per second squared. And then my diameter, 20 centimeters, which I'm going to convert to meters here. Okay, so I'll just throw the divide by 100 in there, which I have the denominator here. So the pressure due to my piston head is going to be equal to m times g divided by pi divided by 4 times d squared. All right, where I've already built in the diameter in centimeters divided by 100. Okay, and that should do it. Okay, so then the total, so let me add in, so the my atmospheric pressure in bar is, well, first let's calculate the pressure head, and then we can take a look at what our conversion is. Okay, so my pressure is 9.3679. 9.3679 times 10 to the 3. Okay, and that's pascals. So that might seem large, it's a large number. Okay, but the key to remember is 1 bar is 1 times 10 to the 5 Pascal. All right, so here's our conversion here. All right, so 1 bar, all right, is 1 times 10 to the 5 pascals. Okay, so I know that 1 bar is equal to 1 times 10 to the 5 pascals. Okay, so if I convert my pressure head to bars, okay, so this is 10 to the 3, so 1, 2, it'll be 0.093679 bars. Okay, so it's really pretty small when I convert to units of bar. So my total pressure, right, we said was equal to the pressure due to that piston head plus atmospheric pressure, or the pressure of my surroundings. And so pressure of my atmosphere we had is 1 bar. All right, so this could be a whopping 1.093679 bar. Okay. So I have more decimal places than I should, but that's okay. And so key here, all right, is that the atmospheric pressure, all right, is much larger than the pressure due to that head. Okay. So my, total external pressure, or P, is equal to 1.093679 bars. All right, so 1.09 bars. Okay, cool. So what's the pressure inside the cylinder? The pressure is equal to my external pressure, which is equal to that. All right, now B. Let's see what we have in B. B says heat is added to the cylinder, causing the gas to expand. The piston rises and finally rests at 50 centimeters above its initial level. How much work was done during this process? All right, so in the first part we calculated pressure, right? We know pressure, and we know, so essentially we just know the initial pressure. Okay, so what we know based on the problem statement and then what we calculate in part A is we know the pressure, right? The pressure is equal to this 1.09 bar. Okay, so I have a piston, so as I expand, right, pressure is being held constant. Okay, so pressure is going to be constant throughout my process. So during this expansion process, pressure is going to be constant and equal to that value we just calculated. we're told that heat's added. We're not told how much heat. We're told heat's added so that the change in height is equal to 50 centimeters. Okay, got it. And we're asked how much work is done. So based on the information given, right, I'm going to assume that the work is done reversibly. Okay, I'm going to assume that we have reversible PV boundary work. Okay, we're not told how much heat's added, and so we're not given any other variables or any other parameters that allow us to characterize our system. So the only way I see solving this is I'm going to assume that my work is reversible. Okay, so if I have reversible boundary work, then W is going to be equal to the integral of negative P dV. Okay, where P is held constant, so I'm going to bring it out of my integral. And I'm going to integrate from some initial to some final state. Okay, A and B is good, but I'm going to use 1 and 2 just because I don't know, I like to think in terms of numbers. So the work required, right, will be the integral from my initial state to my final state of negative P dV, where I have a piston, so pressure is held constant. So I'll bring pressure out and solve the integral from 1 to 2 dV. And so that'll be negative P times V2 minus V1, where V2 is my final volume minus my initial volume. Okay, cool. All right, so let's do it. Okay, so how much work? Yeah, so how much work is done for this expansion process? Only information, so we know P. Okay, so the pressure of my cylinder, right, is this external pressure, which is our 1.093679 bars, okay, which would be 1.093679 times 10 to the 5 pascals. So then the question is, what is V2 and what is V1? Okay. Well, we're not told what the initial volume is. We're told what the difference is. All right, and so let's work in terms of V2 minus V1. Okay. So in general, okay, the volume of my cylinder is going to be equal to what? So it's going to be so it's a cylinder, so I have area of a circle times the height. So it'll be the area of a circle, we just had pi r squared times, I'm going to write hi. So the volume in state I would be equal to area pi r squared. We'll assume we have a constant cross-sectional area equal to the cross-sectional area of that piston head times hi, right, the height at that state I. Okay, so if we simplify this, okay, just as we had before, that's pi times d over 2 squared times, in this case, hi, so that'd be pi over 4 d squared times hi. Okay. So therefore, V2 minus V1 must be equal to pi over 4 d squared times h2 minus h1. All right, so if I plug that in, okay, then I have W is equal to, okay, now remember this is a negative P. Why? Because our sign convention is if our system's doing work on the surroundings, that's negative. If work is being done on our system by the surroundings, that's positive. So if my system's expanding, right, my volume's increasing, my system's doing work on the surroundings. So if I'm expanding, I'm doing work, right, so I need a negative to obey my sign convention. Okay, so W is equal to negative P. Okay, then V2 minus V1. Okay, negative P times pi over 4 d squared times h2 minus h1. All right, so now if we plug in what we know, okay, so I'm going to work in SI units. So now as I work in SI units, I don't know how many moles are in my system, right? We're not told the volume or say initial temperature, you know, it's assuming we have an ideal gas that we could compute it. So PV, right? So when I look at, you know, PdV. Okay, so if I work in pressure and SI units and V, right here, I should note that I'm taking V total to be, say, my extensive volume. Okay, as I expand. So W will also be extensive, right? Be in units. So if I use SI units, will be in units of joules, as compared to a molar unit, right? A molar or specific. Okay, so let me note that this is my total volume. Okay, so W, which is going to be my extensive energy, it's going to be units of energy. It's going to be my work. So I'll work in SI units. So taking inventory. So pressure was our 1.09, 3679 times 10 to the 5 pascals. My diameter again, okay, I'll just write as 20 divided by 100 meters, right? 20 centimeters. And then H2 minus H1. Okay, we're told the change in height. All right, so it rises 50 centimeters. So the change in height would be 50 centimeters, and I'll just write as 50 over 100 meters. Okay, so computing, okay, we get, okay, 2. All right, so what I'll do here, all right, to get this, so let me just compute P head in bars was equal to P head divided by 1 e to the 5. And then I'm going to add that. So P of my surroundings in bars was 1. So my external pressure in bars was my pressure head converted to bars plus the pressure of my atmosphere in bars. So then part 2, okay, first thing I'm going to do is let me convert pressure to pascals. So I'll work in pascals. Okay, diameter I already have in there, and then let me just call it DH. H2 minus H1 was 50. Okay, so the W is going to be equal to negative P, I'm working in pascals, times pi divided by 4 times d squared times that change in height. Okay, so my work would be this, right? Negative 1.7179. Now I used SI units, pressure was in Pascal, and my so my pressure is in Pascal, my volume was in units of meters cubed, and so this is going to be in units of joules. Okay, so the work was negative 1.7179 times 10 to the 3 joules. Okay, or they'd be equivalent to negative 1.71 kilojoules. Okay. All right, and so that's assuming I have reversible PV boundary work, which is the only way I see that we can solve this problem. Okay. C, what is the pressure inside the cylinder at the end of part B? Well, the pressure is unchanged, all right, so the pressure of my cylinder is still going to be equal to our 1.093679 bars. All right, so we have a piston cylinder, so during this expansion process, the pressure is not changing. Okay, so the pressure is constant and equal to this. All right, hopefully that helps. That was a fun one. We'll see you in problem 2.